So we have team overflow from Amrita Vishwavidyapitham, and the problem statement you have selected is SIH 1734, and the title is downscaling of satellite based air quality map using AI or ML. So the solution that we are proposing for monitoring, prediction and alert system is using federated learning. Federated learning leverages ML and DL in a decentralized approach to achieve better robust NO2 air quality maps. So during cloudy conditions, satellite data alone is not sufficient. We take data from the ground stations. These ground station, each of them will act as a node, and what it does is it collects data from its own sensors and from the satellite, and uses an ML or DL model and runs it locally. And what it does is, while running it locally, the data is secure, and it creates a model with weights and biases, and these weights and biases are updated into a network. So what happens is, in this network, as we can see here, all these stations from permanent station 1 to n and the satellite data is collected in a global FL model in a federated learning server, which creates a global FL model. So what the global model FL model does is, it learns from all the weights and biases from all the local stations to create a global model. And what it does is, this acts as an iterative approach, and this global FL model is updated in all the permanent stations on the next day. So what happens is, each and every station is now robust, as it knows what is the data and what is the trend of the NO2 air quality map from all the other stations without even receiving its data. So what it does is, the technology used is front end. We are going to use React.js. Database is NoSQL database to handle large amounts of documents. And the ML or DL model we are going to use is LSTMs or BGRU, which is compatible with modern day FL. Middleware is fast API and backend is Python. So what it does is, each and every permanent station will have its own local model running inside them. It will update the weights and biases into the federated learning server, which creates a global FL model. This global FL model is then updated into each and every permanent station, so that huge amounts of data can be handled. So as we can see here, if we are going to sample the data every 1 second, so the data generated by one station will be huge. So in order to reduce the computational cost and to be more efficient, only the weights and biases will be shared through the network. This network is secure, so that even if a hacker gets their hands on the data, metadata that is being passed through the network, without the actual data from the data's permanent stations, they cannot make any sense of it. So that is the feasibility and viability of the idea. Ground-based stations and satellite data readily available. Integration with IoT sensors allow continuous data collection. Model development. The federated learning approach is feasible with the current technologies like BGRU and LSTM models. The potential challenging and risk is syncing problem. The data collection and syncing. Real-time synchronization between satellite and ground stations may face delays, and variability in data from different locations may affect model accuracy, because the data distribution, as the sampling rate might differ, the data distribution is not equal, so that it might affect the model. So the strategies for overcoming these challenges is that there is a method in a federated learning data aggregation type, which is called as personalized fed average, which assigns weight and importance based upon the amount of data each node is trained on, and it personalizes for each device post training and updates its local model. So what happens is, asynchronously each and every node will update its weights and biases along with how much data it has been trained on, and the global model will be updated to the nodes on the next day. So if a node is placed in an unknown location or in a new environment, first it will perform based upon the previous data collected from all the other places, which is in the form of the global model, and then when it collects its own data in its new environment, the global model will be updated locally, and it will create its own local model which performs better for that location. And we know the impact: environmental, social and economic. The benefits is, personalized FL model can adapt to unseen environments. It can be scaled infinitely, as if we want to scale it to a new area, we can just place a permanent station node there. Iterative improvement ensures that the iterative nature of FL model leads to a steady increase in the prediction accuracy over time, as the local models get more and more data. Security: data is generated as secure in the network, as model weights alone is transferred, and it won't make sense to an intruder without any data points. Thank you.